one okay, no problem. It's a technical support data. Great. Dear students, welcome to the class. Let me continue from the last class. So in the last class, we learned about the condition for a molecule which must be satisfied to be optically active. That is, the absence of plane of symmetry is the primary and necessary condition for any molecule to be optically active. After that, the next the fundamental concept is chiral molecule. To call a molecule as a chiral molecule, we need to know about the three symmetry elements. The first one is plane of symmetry. Plane of symmetry. The second one is center of symmetry. Center of symmetry. The third and also the last one is axis of symmetry. Axis of symmetry. Remember, plane of symmetry, center of symmetry, and axis of symmetry are more commonly generally known as elements of symmetry. I mean to say there are three elements of symmetry, namely plane of symmetry, center of symmetry, and axis of symmetry. And we have learned something about plane of symmetry in the last class. That is, plane of symmetry is an imaginary plane which divides the molecule into two identical halves, not two halves. Please remember, it must divide the molecule into two identical halves. The second one is the two halves must be related with each other as an object and mirror image. And the third one is they must be non-superimposable one on one another. And when we place the two halves on one over the other, the identical groups should not sit one over the other. So any molecule which divides the molecule into two identical halves, which are related with each other as an object and mirror image, which are non-superimposable or with one another, that when these three conditions are satisfied, then we used to say that the molecule is having a plane of symmetry. That plane of symmetry should be absent. I mean to say the absence of plane of symmetry is the one primary and necessary condition for any molecule to be optically active. So the second one is center of symmetry. To learn about center of symmetry, now let me consider one example, that is tartaric acid. Tartaric acid, very simple, tartaric acid. Tartaric acid is the one which is having the following structure. Remember, this is COH, look here, C, and one more COH, and let me take, this is OH, and this one is OH, and H. This is one of the structure of tartaric acid. We are able to write a force structure to the given molecule because for any molecule, the number of possible isomers depends upon the number of chiral carbon atoms. That is according to Van 't Hoff rule. Van 't Hoff rule. Remember, Van 't Hoff rule is nothing but 2 to the power of n. Very simple. 2 to the power of n. This is the one which gives the number of possible isomers for a given molecule, where n is the number of chiral carbon. Please, n is the number of chiral carbon, not the carbon atom. Though tartaric acid is having 4 carbon atoms, remember, out of 4 carbon atoms, there are only 2 chiral carbon atoms. This is chiral carbon atom, and this is also a chiral carbon atom. A carbon atom which is having either a double bond or a triple bond will never be chiral. So that in tartaric acid, though there are 4 carbon atoms, there are only 2 chiral carbon atoms. As the chiral carbon atoms are only 2 in number, the value of n is 2 in number. Therefore, 2 to the power of 2, that is equal to 4 isomers are possible for your tartaric acid. Out of 4 different structures, only one structure is on the board now. In this particular one of the structure of tartaric acid, let me select one particular point. This is the one point which I have selected. Selecting one particular center point in the molecule. When we move one particular point in the now select the center point in the when we move equal distance in opposite direction. Remember, in opposite direction means, remember, when we move like this, the opposite direction should also be in this particular manner. That is with an angle of 180 degree. So, starting from one particular point, when we move equal distance in opposite direction, in such case, when we are able to meet the identical atoms or groups, then we used to say that the molecule is having a center of symmetry. ಒಂದು ಮಾಲಿಕ್ಯೂಲ್ಗೆ ಸೆಂಟರ್ ಆಫ್ ಸಿಮೆಟ್ರಿ ಇದೆ ಅಂತ ನಾವು ಹೇಳಬೇಕು ಅಂದ್ರೆ ಒಂದು ಸೆಂಟರ್ ಪಾಯಿಂಟ್ ಅನ್ನು ನಾವು ಸೆಲೆಕ್ಟ್ ಮಾಡಿ ಆ ಸೆಲೆಕ್ಟ್ ಮಾಡಿರ್ತಕ್ಕಂಥ ಪಾಯಿಂಟ್ ಇಂದ ಈಕ್ವಲ್ ಡಿಸ್ಟೆನ್ಸ್ ಆಪೋಸಿಟ್ ಡೈರೆಕ್ಷನ್ ಮೂವ್ ಆದಾಗ ಸಿಮಿಲರ್ ಆಟಮ್ಸ್ ಮತ್ತೆ ಗ್ರೂಪ್ಸ್ ನಾವೇನಾದ್ರೂ ಮೀಟ್ ಮಾಡೋದಾದ್ರೆ ಆಗ ಆ ಮಾಲಿಕ್ಯೂಲ್ಗೆ ಸೆಂಟರ್ ಆಫ್ ಸಿಮೆಟ್ರಿ ಇದೆ ಅಂತ ಹೇಳ್ತೀವಿ. ಟು ಸೇ ದಟ್ ದ ಮಾಲಿಕ್ಯೂಲ್ ಇಸ್ ಹ್ಯಾವಿಂಗ್ ಎ ಸೆಂಟರ್ ಆಫ್ ಸಿಮೆಟ್ರಿ, after selecting one center point in the given molecule, we will move equal distance. Look here, when we move towards this direction, we are meeting one OH group. In the opposite direction, we are meeting again the similar type of OH group. When we move in this direction, we will meet hydrogen atom. In this direction, we will also meet the hydrogen atom. From this point, when we move towards this, we will meet this particular COOH group. From this point, when we move in this opposite direction, we will also meet the similar type of group. So that from this particular point, when we move equal distance in opposite direction, we are meeting the identical atoms and groups. Then we used to say that this structure or this one particular structure of tartaric acid is having a center of symmetry. For any molecule, there may be any number of plane of symmetry, there may be any number of axis of symmetry, but if there is a center of symmetry for a given molecule, the center of symmetry is only one. ಒಂದು ಮಾಲಿಕ್ಯೂಲ್ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮೆಟ್ರಿ ಬೇಕಾದ್ರೆ ಎಷ್ಟಾದ್ರೂ ಇರಬಹುದು, ಆಕ್ಸಿಸ್ ಆಫ್ ಸಿಮೆಟ್ರಿ ಬೇಕಾದ್ರೆ ಎಷ್ಟಾದ್ರೂ ಇರಬಹುದು, ಬಟ್ ಸೆಂಟರ್ ಆಫ್ ಸಿಮೆಟ್ರಿ ಅಂತ ಏನಾದ್ರು ಇದ್ರೆ ಸೆಂಟರ್ ಆಫ್ ಸಿಮೆಟ್ರಿ ಒಂದೇ ಒಂದಿರುತ್ತೆ. ಹಾಗಾದ್ರೆ ಸೆಂಟರ್ ಆಫ್ ಸಿಮೆಟ್ರಿ ಇದೆ ಅಂತ ನಾವು ಯಾವಾಗ ಹೇಳ್ತೀವಿ ಅಂದ್ರೆ ಆ ಮಾಲಿಕ್ಯೂಲ್ ಒಂದು ಸೆಂಟರ್ ಪಾಯಿಂಟ್ ಅನ್ನ ಸೆಲೆಕ್ಟ್ ಮಾಡಿ ಆ ಸೆಂಟರ್ ಪಾಯಿಂಟ್ ಇಂದ ಈಕ್ವಲ್ ಡಿಸ್ಟೆನ್ಸ್ ಆಪೋಸಿಟ್ ಡೈರೆಕ್ಷನ್ ಮೂವ್ ಆದಾಗ ಐಡೆಂಟಿಕಲ್ ಆಗಿರ್ತಕ್ಕಂಥ ಆಟಮ್ಸ್ ಮತ್ತೆ ಗ್ರೂಪ್ಸ್ ನಾವೇನಾದ್ರೂ ಮೀಟ್ ಮಾಡೋದಾದ್ರೆ ಆಗ ಆ ಮಾಲಿಕ್ಯೂಲ್ಗೆ ಸೆಂಟರ್ ಆಫ್ ಸಿಮೆಟ್ರಿ ಇದೆ. ಐ ಹೋಪ್ ಇಟ್ ಇಸ್ ಕ್ಲಿಯರ್. Starting from one center point in the given molecule, when we move equal distance in the opposite direction, when we are able to meet the identical atoms or groups, then the molecule is said to possess center of symmetry. So after knowing plane of symmetry and center of symmetry, the third one is axis of symmetry. Axis of symmetry to decide whether the given molecule is having an axis of symmetry or not. Now take the molecule and rotate the molecule around an axis. See, there are three axes: x-axis, y-axis, and z-axis. You can rotate the molecule, see, around x-axis, or you can rotate the molecule around y-axis, or you can rotate the molecule around z-axis. So, we ask you to rotate. Andre, one axis sutta molecule na rotate ಮಾಡಿ. One axis sutta molecule na rotate ಮಾಡಬೇಕಾದ್ರೆ you can rotate the molecule around x-axis, need not be x-axis only. You can also rotate the molecule around y-axis, or you can also rotate the molecule around z-axis. Like that, when we rotate the molecule around one particular axis, within 360-degree rotation, if the similar atoms or groups, if they reappears, then we used to say that the molecule is having an axis of symmetry. So that to have or to say that the molecule is having an axis of symmetry, the similar atoms or groups must reappear within 360-degree rotation. Within 360-degree rotation, when the similar atoms or groups reappears, when we rotate a molecule around one particular selected axis, then we used to say that the molecule is having an axis of symmetry. Let me select one particular example. Remember, so this is what. Now I am going to take one simple example. So this is what the molecule. So this is the molecule which is known as lactic acid. Lactic acid. Remember, so I have selected one molecule by name lactic acid. Lactic acid is the one molecule which contains 3 carbon atoms, 1, 2, and 3. Of the 3 carbon atoms, you know very well. So this is the carbon atom which I am going to mark by star is the chiral carbon atom. This is the carbon atom which is bonded to 4 different atoms and groups. Hydrogen is different, COH group is different, OH group is different, CH3 is different. When this particular carbon atom is bonded to 4 different atoms or groups, I can call this carbon as a chiral carbon. That is the chiral carbon. Remember, as this particular carbon atom is bonded to 4 different atoms or groups, when we try to divide the molecule through any plane which is passing through the center, we will never get 2 identical halves. When we are not able to get 2 identical halves, when we divide the molecule through any plane, this particular molecule is not having a plane of symmetry. ಹಾಗಾದ್ರೆ ಇದನ್ನು ಯಾವುದೇ ಪ್ಲೇನ್ ಅಲ್ಲಿ ನಾವು ಕಟ್ ಮಾಡಿದ್ರು ಸಹ ನಮಗೆ 2 ಐಡೆಂಟಿಕಲ್ ಹಾಫ್ ಬರಲ್ಲ. 2 ಐಡೆಂಟಿಕಲ್ ಹಾಫ್ ಬರಲ್ಲ ಅಂತಂದ್ರೆ ನಮ್ಮ ಲ್ಯಾಕ್ಟಿಕ್ ಆಸಿಡ್ ಮಾಲಿಕ್ಯೂಲ್ಗೆ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮೆಟ್ರಿ ಇಲ್ಲ. Next, coming to examine the center of symmetry. Remember, starting this particular point, from one particular point, when we move equal distance in opposite direction, we will never meet the identical atoms or groups. Then the molecule is not having a center of symmetry. Let me have the same molecule of lactic acid in a tetrahedral manner. Then it is very easy for our discussion. Actually, the molecule should be as follows. This is the one. This should be taken like this, and like this, and this is the tetrahedral shape of the molecule. Let me take it as this is OH, and this one is H, and this one is CH3, and let me take it as this is COOH. Right? Okay. ಡಿವೈಡ್ ಮಾಡೋಣ. ಯಾವುದೇ ಪ್ಲೇನ್ ಅಲ್ಲಿ ನೀವು ಕಟ್ ಮಾಡಿದ್ರು ಸಹ ನಮಗೆ 2 ಐಡೆಂಟಿಕಲ್ ಹಾಫ್ ಬರ್ತಾ ಇಲ್ಲ ಅಂತಂದ್ರೆ ಈ ಮಾಲಿಕ್ಯೂಲ್ಗೆ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇಲ್ಲ. ಎರಡನೇ ಸೆಂಟರ್ ಆಫ್ ಸಿಮಿಟ್ರಿನ ಎಕ್ಸಾಮಿನ್ ಮಾಡೋಣ. ನೋಡಿ ಒಂದು ನಿಮಿಷ. ಈ ಪಾಯಿಂಟ್ ಇಂದ ನಾವೇನಾದ್ರೂ ಮೂವ್ ಆಗಿ ಈಕ್ವಲ್ ಡಿಸ್ಟೆನ್ಸ್ ಆಪೋಸಿಟ್ ಡೈರೆಕ್ಷನ್ ಮೂವ್ ಆದ್ರೆ, when we move equal distance in opposite direction, it is not possible to meet the identical atoms or groups. Then the molecule is not having a center of symmetry. Center of symmetry ಸಹ ಇದಕ್ಕೆ ಇಲ್ಲ. ಆಕ್ಸಿಸ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಚೆಕ್ ಮಾಡಕ್ಕೆ ಅಂತ ಹೊರಟ್ರೆ ನೋಡಿ ಒಂದು ನಿಮಿಷ. ನಮಗೆ OH ಮಾಲಿಕ್ಯೂಲ್ OH ಗ್ರೂಪ್ ಕಾಣ್ತಾ ಇದೆ ಅಂತ ತಿಳ್ಕೊಳ್ಳಿ. ನೀವೇನಾದ್ರೂ ರೊಟೇಟ್ ಮಾಡ್ತಾ ಬಂದ್ರೆ ನಿಮಗೆ 360 ಡಿಗ್ರಿ ರೊಟೇಟ್ ಆಗೋದರ ಒಳಗೆ ನಿಮಗೆ ಅಂತದೇ ಇನ್ನೊಂದು OH ಗ್ರೂಪ್ ಕಾಣಬೇಕು ಅಂದ್ರೆ ಇನ್ನೊಂದು OH ಗ್ರೂಪ್ ಅಲ್ಲಿ ಇರಬೇಕಿತ್ತು. ಇರದೇ ಒಂದು OH ಅಂತಂದ್ರೆ ನೀವು ರೊಟೇಟ್ ಮಾಡ್ತಾ ಬಂದಾಗ, when you rotate the molecule, so the same OH group reappears after 360 degree rotation, and within 360 degree rotation the similar groups will never reappear because there are no 2 identical groups at all in the molecule. ಹಾಗಾದ್ರೆ ಒಂದೇ ತರ ಗ್ರೂಪ್ ಅಲ್ಲಿ ಎರಡಿಲ್ಲ. CH3 ಇರದೇ ಒಂದು, H ಇರದೇ ಒಂದು, OH ಇರದೇ ಒಂದು, COH ಇರದೇ ಒಂದು. ನೀವು ಯಾವುದೇ ಗ್ರೂಪ್ ನ ರೆಫರೆನ್ಸ್ ಇಟ್ಕೊಂಡು ರೊಟೇಟ್ ಮಾಡ್ತಾ ಬಂದ್ರೆ, ಒಂದು ಗ್ರೂಪ್ ನ ರೆಫರೆನ್ಸ್ ಇಟ್ಕೊಳ್ಳಿ, COH ಕಾಣ್ತಾ ಇದೆ, ತಿರುಗಿಸ್ತಾ ಬಂದ್ರೆ 360 ಬಂದಾಗ ಅದೇ COH ಕಾಣುತ್ತೆ ಹೊರತು ಅಂತದ್ದು ಇನ್ನೊಂದು COH ಕಾಣ್ಲಿಕ್ಕೆ ಅಲ್ಲವೇ ಇನ್ನೊಂದು COH ಇಲ್ಲ. As the similar groups will never reappear within 360 degree rotation. Of course, after 360 degree rotation the same group will appear. No, that is not the one we are observing. Within 360 degrees the identical reappearance of the group must be there to say that the molecule is having an axis of symmetry. Since the similar groups will never reappear within 360 degree rotation, the molecule is not having even axis of symmetry. 360 ಡಿಗ್ರಿ ತಿರುಗೋದರ ಒಳಗೆ ಒಂದೇ ತರ ಗ್ರೂಪ್ಸ್ ರಿಅಪಿಯರ್ ಆಗಲ್ಲ. ಒಂದೇ ತರ ಗ್ರೂಪ್ಸ್ ರಿಅಪಿಯರ್ ಆಗಲ್ಲ ಅಂದ್ರೆ ಅದಕ್ಕೆ ಆಕ್ಸಿಸ್ ಆಫ್ ಸಿಮಿಟ್ರಿನೂ ಇಲ್ಲ. ಹಾಗಾದ್ರೆ ನಾವು ಸೆಲೆಕ್ಟ್ ಮಾಡಿರ್ತಕ್ಕಂಥ ಲ್ಯಾಕ್ಟಿಕ್ ಆಸಿಡ್ಗೆ ಒಂದು ಯಾವುದೇ ಪ್ಲೇನ್ ಅಲ್ಲಿ ಕಟ್ ಮಾಡಿದ್ರು ಸಹ 2 ಐಡೆಂಟಿಕಲ್ ಹಾಫ್ ಬರಲ್ಲ ಅಂದ್ರೆ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇಲ್ಲ. ನಾವು ಸೆಂಟರ್ ಇಂದ ಈಕ್ವಲ್ ಡಿಸ್ಟೆನ್ಸ್ ಆಪೋಸಿಟ್ ಡೈರೆಕ್ಷನ್ ಮೂವ್ ಆದಾಗ ಐಡೆಂಟಿಕಲ್ ಗ್ರೂಪ್ಸ್ ಮೀಟ್ ಆಗಲ್ಲ ಅಂದ್ರೆ ಸೆಂಟರ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇಲ್ಲ. ನಾವು ಈ ಮಾಲಿಕ್ಯೂಲ್ ನ ಒಂದು ಆಕ್ಸಿಸ್ ಸುತ್ತ ರೊಟೇಟ್ ಮಾಡಿದಾಗ 360 ಡಿಗ್ರಿ ತಿರುಗುವುದರ ಒಳಗೆ ಸಿಮಿಲರ್ ಗ್ರೂಪ್ಸ್ ರಿಅಪಿಯರ್ ಆಗಲ್ಲ ಅಂದ್ರೆ ಆಕ್ಸಿಸ್ ಆಫ್ ಸಿಮಿಟ್ರಿನೂ ಇಲ್ಲ. ಸೊ ದಟ್ for a molecule like lactic acid, there is no plane of symmetry, there is no center of symmetry, there is no axis of symmetry. I mean to say all the 3 symmetry elements are absent. ಹಾಗಾದ್ರೆ 3 symmetry elements ಇದಾವಲ್ಲ, plane of symmetry, center of symmetry, axis of symmetry ಅಂತ, ಈ ಮೂರಲ್ಲಿ ಯಾವುದು ಇಲ್ಲ? 3 ಇಲ್ಲ. ಸಿಂಪಲ್ ಆಗಿ ನಾವು ಇದು 3 ಬಿಟ್ಟಿದ್ದು. I hope you can understand. A very simple manner to remember. ಯಾವ ಮಾಲಿಕ್ಯೂಲ್ 3 ಬಿಟ್ ತರ ಬಿಹೇವ್ ಮಾಡುತ್ತೋ, ಯಾವ ಮಾಲಿಕ್ಯೂಲ್ಗೆ 3 ಅಬ್ಸೆಂಟ್ ಆಗಿರುತ್ತೋ, ಯಾವ ಮಾಲಿಕ್ಯೂಲ್ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ, ಸೆಂಟರ್ ಆಫ್ ಸಿಮಿಟ್ರಿ, ಆಕ್ಸಿಸ್ ಆಫ್ ಸಿಮಿಟ್ರಿ 3 ಅಬ್ಸೆಂಟ್ ಆಗಿರುತ್ತೋ ಆ ಮಾಲಿಕ್ಯೂಲ್ ನೇ ನಾವು ಕರೆದಿದ್ದು ಕೈರಾಲ್ ಮಾಲಿಕ್ಯೂಲ್. I hope you can understand this. ಹಾಗಾದ್ರೆ ಯಾವುದೇ ಮಾಲಿಕ್ಯೂಲ್ ಅನ್ನು ನೀವು ಕೈರಾಲ್ ಮಾಲಿಕ್ಯೂಲ್ ಅಂತ ಕರಿಬೇಕು ಅಂದ್ರೆ ಅದಕ್ಕೆ ಮೂರು ಸಿಮಿಟ್ರಿ ಎಲಿಮೆಂಟ್ಸ್ ಆಬ್ಸೆಂಟ್ ಆಗಿರಬೇಕು. ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಆಬ್ಸೆಂಟ್ ಆಗಬೇಕು, ಸೆಂಟರ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಆಬ್ಸೆಂಟ್ ಆಗಬೇಕು, ಆಕ್ಸಿಸ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಆಬ್ಸೆಂಟ್ ಆಗಬೇಕು. Any molecule for which all the three symmetry elements are absent, such molecules are called chiral molecules. Then lactic acid is a chiral molecule because all the three symmetry elements are absent. Now, next simple question is whether such chiral molecules are actually active or not. That can be decided very easily. Our condition for any molecule to be optically active is absence of plane of symmetry. ಹೌದು, ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇರಬಾರ್ದು. ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇರಬಾರ್ದು ಅಂತ ಏನು ನಾವು ಕಂಡೀಷನ್ ಹೇಳ್ತಾ ಇದೀವಿ, ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇಲ್ಲ. ಹಾಗಾದ್ರೆ ಆಪ್ಟಿಕಲಿ ಆಕ್ಟಿವ್ ಆಗಬೇಕು ಅಂದ್ರೆ ಸೆಂಟರ್ ಆಫ್ ಸಿಮಿಟ್ರಿ, ಆಕ್ಸಿಸ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇರಬೇಕು ಇರಬಾರ್ದು ಅನ್ನೋ ನಮ್ಮ ಕಂಡೀಷನ್ ಅಲ್ಲಿ ಇಲ್ಲವೇ ಇಲ್ಲ. Absence of plane of symmetry is the one and only primary and necessary condition ಅಂತ ಮಾತಾಡಿದ್ವಿ. ಹಾಗಾದ್ರೆ ಲ್ಯಾಕ್ಟಿಕ್ ಆಸಿಡ್ ಮಾಲಿಕ್ಯೂಲ್ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇಲ್ಲ ಅಂದ್ರೆ that particular molecule, chiral molecule, is optically active. All chiral molecules are optically active. It is because of the absence of plane of symmetry. Now, after knowing the chiral molecule, ಗೊತ್ತಾಯ್ತು chiral molecule ಅಂತಂದ್ರೆ ಮೂರು ಸಿಮಿಟ್ರಿ ಎಲಿಮೆಂಟ್ಸ್ ಅಲ್ಲಿ ಯಾವ್ದು ಇರಬಾರ್ದು, ಮೂರು ಇರಬಾರ್ದು, ಪ್ಲೇನ್ ಇರಬಾರ್ದು, ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇರಬಾರ್ದು, ಸೆಂಟರ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇರಬಾರ್ದು, ಆಕ್ಸಿಸ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇರಬಾರ್ದು. ಹಾಗಾದ್ರೆ ಮೂರಾಗಿ ಎಷ್ಟು ಬಿಡಬೇಕು, ಮೂರು ಬಿಡಬೇಕು. ಮೂರು ಬಿಟ್ಟಿದೆ ಅಂತ ಅಂದ್ರೆ ಆ ಮಾಲಿಕ್ಯೂಲ್ ಕೈರಾಲ್ ಮಾಲಿಕ್ಯೂಲ್ ಅಂತ ಕರಿತೀವಿ. ಕೈರಾಲ್ ಮಾಲಿಕ್ಯೂಲ್ ಆಪ್ಟಿಕಲಿ ಆಕ್ಟಿವ್ ಆಗಿರುತ್ತಾ ಸರ್? 100%. ಯಾಕೆ ಸರ್ ಅಂದ್ರೆ ಆಪ್ಟಿಕಲಿ ಆಕ್ಟಿವ್ ಆಗಬೇಕು ಅಂದ್ರೆ ಏನ್ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಆಬ್ಸೆಂಟ್ ಇರಬೇಕಿತ್ತು, ಇದೆ. As the molecule does not possess plane of symmetry, it becomes optically active. Now, coming to Van flow, as the lactic acid molecule is having only one chiral carbon atom, only one chiral carbon atom, the value of n is equal to 1. Then 2 to the power of 1 is equal to 2. 2 to the power of 1 is equal to 2 means for a lactic acid molecule, we are able to write 2 isomers. 2 isomers ಅಂತಂದ್ರೆ ಯಾವುದು ಸರ್? ಅದರಲ್ಲಿ ಒಂದು ಬೋರ್ಡ್ ಮೇಲಿದೆ. ಈಗ ಎರಡನೇ ಐಸೋಮರ್ ನಮಗೆ ಬರೆಯೋಣ. So the second isomer is the mirror image of this particular molecule. When you observe the same molecule in mirror, it looks like this. So remember, it looks absolutely like this. This becomes OH, this becomes CH, this becomes CH3, whereas this one becomes COOH. So these two molecules are the object and mirror images. So the two possible structures for a given lactic acid molecule according to Van flow, as the molecule contains only one chiral carbon atom, molecule only one chiral carbon ಇದೆ, ಒಂದೇ ಒಂದು chiral carbon ಇದೆ ಅಂದ್ರೆ value of n is equal to 1. When n is equal to 1, the 2 to the power of 1, 2 to the power of 1 is equal to 2 ಅಂತ ಅಂದ್ರೆ lactic acid molecule ಗೆ ನಾವು ಎರಡು ಸ್ಟ್ರಕ್ಚರ್ ನ ಬರೆಯಬಹುದು. So both the structures are on the board now. So this is structure 1 and structure 2. Now look into the different properties of the molecule. Now let me take this is the structure 1 and this is the structure 2. So structure 1 and structure 2 are the object and mirror images of your lactic acid. Now any molecules, remember these two molecules are having identical chemical formula, identical chemical composition, identical structure. Both of them are tetrahedral structure and they are having similar physical and chemical properties. But remember, because of the absence of plane of symmetry, both of them are optically active. And when structure 1 rotates the plane polarizer light in one direction, the mirror image of the structure 1, that is nothing but your structure 2, always rotates the plane polarizer light in the opposite direction with the same angle. I mean to say, let us take structure 1 is dextrorotatory, which rotates the plane polarizer light in the clockwise direction to an extent of something like 70 degrees. It is just a mere number I am taking as an example. Don't confine to that number. There is 70 degrees ಅಂತ ನಾನು ಹೇಳಿದ್ದೀನಿ, ಅದನ್ನ ಹಿಡ್ಕೊಂಡ್ಬಿಡ್ಬೇಡಿ, ಅದನ್ನ ಎಕ್ಸಾಂಪಲ್ ಆಗಿ ಮಾತ್ರ ಸೆಲೆಕ್ಟ್ ಮಾಡ್ತಾರೆ. ಸೊ ಇದು ಡೆಕ್ಸ್ಟ್ರೋರೊಟೇಟರಿ ರೈಟಿಂಗ್ ರೊಟೇಟ್ ಮಾಡುತ್ತೆ, 70 ಡಿಗ್ರಿ ರೊಟೇಟ್ ಮಾಡುತ್ತೆ ಅಂತಂದ್ರೆ 100% ಸ್ಟ್ರಕ್ಚರ್ 2 ಲಿವೋ ರೊಟೇಟರಿನೇ ಆಗಿರುತ್ತೆ. ಬಟ್ ದ ಆಂಗಲ್ ಆಫ್ ರೊಟೇಷನ್ ಇಸ್ ಸೇಮ್, ದಟ್ ಇಸ್ 70 ಡಿಗ್ರಿ, ಬಟ್ ಇನ್ ದ ಆಂಟಿ ಕ್ಲಾಕ್ವೈಸ್ ಡೈರೆಕ್ಷನ್ ಟುವರ್ಡ್ಸ್ ಲೆಫ್ಟ್. ಹಾಗಾದ್ರೆ compounds with same molecular formula, same chemical composition, same structural formula, same physical and chemical properties, but differing the direction of rotating the plane polarizer light are called optical isomers. Then structure 1 and structure 2 of lactic acid are the optical isomers. Then a pair of, because we have two structures, the two structures I will take as a pair of optical isomers. First condition, these two are a pair of optical isomers. The second condition is related with each other as an object and mirror image. Structure 1 is an object, then structure 2 is a mirror image. If the structure 2 is an object, then the structure 1 is its mirror image. So that they are related with each other as an object and mirror image, and they are non-superimposable on one another. If you just push the molecule and try to keep the structure 2 over structure 1, remember, over the OH, the H will be placed, not OH will be placed. Over the H, OH will be placed, not the H. I mean, the similar groups will not sit one over the other. Therefore, such molecules are said to be non-superimposable on one another. ಒಂದೇ ತರ ಗ್ರೂಪ್ ಒಂದರ ಮೇಲೆ ಕೂತ್ಕೋತಾ ಇಲ್ಲ. OH ಮೇಲೆ ಬಂದು H ಕೂತ್ಕೊಳ್ಳುತ್ತೆ, ಈ H ಮೇಲೆ ಬಂದು OH ಕೂತ್ಕೊಳ್ಳುತ್ತೆ. ಒಂದೇ ತರ ಗ್ರೂಪ್ ಒಂದೊಂದ್ರ ಮೇಲೆ ಒಂದೇ ತರ ಗ್ರೂಪ್ ಒಂದರ ಮೇಲೆ ಕೂತ್ಕೊಳ್ತಾ ಇಲ್ಲ ಅಂದ್ರೆ ನಾನ್ ಸೂಪರ್ ಇಂಪೋಸಬಲ್ ಅಂತ ಕರಿತೀವಿ. ಒಂದೇ ತರ ಗ್ರೂಪ್ ಒಂದರ ಮೇಲೆ ಏನಾದ್ರೂ ಕೂತ್ರೆ ಸೂಪರ್ ಇಂಪೋಸಬಲ್ ಅಂತ ಕರಿತಿದ್ವಿ. ಈಗ as the similar groups, they do not place one over the other, their structure 1 and structure 2 are non-superimposable on one another. So let me take the three conditions one by one in a very discrete manner. So these two, structure 1 and structure 2, are the optical isomers. Please, a pair of optical isomers, a pair of optical isomers which are related with each other as an object and mirror image, which are non-superimposable on one another, are called enantiomers. Please, very important. Structure 1 and structure 2 are the examples of enantiomers. To call two isomers as enantiomers, they have to satisfy the following three conditions. The two molecules must be optical isomers. They must be related with each other as an object and mirror image, and they should be non-superimposable on one another. Any two structures or any two compounds or any two molecules which satisfies these three conditions are termed or named as enantiomers. Enantiomers can be defined as a pair of optical isomers which are related with each other as an object and mirror image and non-superimposable on one another are called enantiomers. Now, let me take structure 1 is something like dextrorotatory, which is denoted by a sign plus, and the structure 2 becomes, that is levorotatory, which is denoted by a sign minus. Another plus lactic acid and minus lactic acid are the examples of enantiomers because they are the optical isomers which are related with each other as an object and mirror image, and they are non-superimposable on one another. Any two compounds or molecules which satisfies these three, I mean to say a pair of optical isomers which must be related with each other as an object and mirror image, and which are non-superimposable on one another are called enantiomers. So the simple example, plus lactic acid and minus lactic acid are the examples of enantiomers. I hope you understand the meaning of enantiomers, and conditions must be satisfied to call the compounds as enantiomers. A pair of optical isomers related with each other as an object and mirror image and non-superimposable on one another are called enantiomers. Examples, plus lactic acid and minus lactic acid are the examples of enantiomers. Now, enantiomers, they rotate the plane polarized light to the same extent but in opposite direction. At the time of determining the angle of rotation of an optically active compound, remember, we have to carry out or we have to conduct the experiment with a certain set of conditions. And with a certain set of conditions, when we determine the angle of rotation, that the angle of rotation which is caused by an optically active compound with a set of conditions is called specific rotation. Specific rotation. Remember, very interesting. Specific rotation. Look here. Specific rotation. Specific rotation is generally denoted by a symbol, something like this. Let us see. Specific rotation is the ratio of alpha divided by L into C. Let me see what does alpha represents, what does L represents, what does C represents. Let us see in detail. So before that, let us study about the meaning or definition of specific rotation. See, when a molecule is not having a plane of symmetry, then we used to say that the molecule is optically active. Then, when a molecule becomes optically active, the next question is, towards which direction it rotates the plane polarized light. I mean, we want to know the direction of rotation and we want to know the angle rotated by the optically active compound. I mean to say, we need two information, the direction of rotation and the angle of rotation. The direction and the angle of rotation of an optically active compound are determined by using an instrument called polarimetry. While determining the direction of rotation and the angle of rotation of an optically active compound by using an instrument called polarimeter, we need to satisfy or we need to follow the following four conditions. We have to prepare a solution of the given compound by dissolving the given compound in a suitable solvent such that the concentration of the solution should be 1 gram per cm cube. 1 gram per cm cube. So, by this, you have to dissolve the given compound in a suitable solvent and the resulting solution should have a definite concentration. The concentration of the solution should be 1 gram per cm cube in such a way that we need to prepare a solution by dissolving the given optically active compound in a particular solvent in which it is soluble. Adre kottanta compound anna one solvent alli dissolve ಮಾಡಿ ಒಂದು solution ಮಾಡಿ solution ಹೆಂಗೆ ಮಾಡಂಗಿಲ್ಲ. ನಾವು ಪ್ರಿಪೇರ್ ಮಾಡತಕ್ಕಂತ ಸೊಲ್ಯೂಷನ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ 1 ಗ್ರಾಮ್ per cm cube ಇರಬೇಕು. ಎರಡನೇ ಕಂಡೀಷನ್, after preparing a solution with a concentration of 1 gram per cm cube, we have to fill that solution into a tube which is present in the polarimeter in such a way that the length of the solution should be 1 decimeter. 1 decimeter should be length of the solution. Polarimeter ಒಂದು ಟ್ಯೂಬ್ ಇರುತ್ತೆ, ಆ ಟ್ಯೂಬ್ ಅಲ್ಲಿ ಸೊಲ್ಯೂಷನ್ ಹಿಂಗೆ ಎಳ್ಕೊತೀವಿ. ಎಳ್ಕೊಂಡಾಗ ಆ ಸೊಲ್ಯೂಷನ್ ಲೆಂತ್ ಯಾವ ರೀತಿ ಅಡ್ಜಸ್ಟ್ ಮಾಡಬೇಕು ಅಂದ್ರೆ ಲೆಂತ್ ಆಫ್ ದಿ ಸೊಲ್ಯೂಷನ್ ಶುಡ್ ಬಿ 1 decimeter ಕರೆಕ್ಟ್ ಆಗಿರಬೇಕು. ಕಾನ್ಸಂಟ್ರೇಷನ್ 1 ಗ್ರಾಮ್ per cm cube ಇರೋ ತರನೇ ಸೊಲ್ಯೂಷನ್ ಪ್ರಿಪೇರ್ ಮಾಡಬೇಕು. ಸೊಲ್ಯೂಷನ್ ಪ್ರಿಪೇರ್ ಮಾಡಬೇಕಾದ್ರೆ ಕೊಟ್ಟಿರೋ ಕಾಂಪೌಂಡ್ ಅನ್ನು ಒಂದು ಸೂಟಬಲ್ ಸಾಲ್ವೆಂಟ್ ಡಿಸಾಲ್ವ್ ಮಾಡಿ ಸೊಲ್ಯೂಷನ್ ಮಾಡ್ತೀವಲ್ಲ, ಆ ಸೊಲ್ಯೂಷನ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಎಕ್ಸಾಕ್ಟ್ ಆಗಿ ಎಷ್ಟೇ ಇರಬೇಕು. ಆ ಸೊಲ್ಯೂಷನ್ ಅನ್ನು ತುಂಬಬೇಕಾದ್ರೆ polarimeter ಇರೋ ಟ್ಯೂಬ್ ಅಲ್ಲಿ the length of the solution should be 1 decimeter and whatever the plane polarized light you are using to conduct the experiment should have a definite wavelength which is denoted by a symbol lambda, and at the time of doing the experiment the temperature should remain constant. There must not be fluctuation in the temperature. So these are the four conditions which we need to follow at the time of determining the direction of rotation and the angle of rotation. ಈ ನಾಲ್ಕು ಕಂಡೀಷನ್ ಅನ್ನು ನಾವು ಕರೆಕ್ಟ್ ಆಗಿ ಫಾಲೋ ಮಾಡಿ ಆ ಒಂದು ಆಪ್ಟಿಕಲಿ ಆಕ್ಟಿವ್ ಕಾಂಪೌಂಡ್ ಎಷ್ಟು ಡಿಗ್ರಿ ರೊಟೇಟ್ ಮಾಡುತ್ತೆ ಅನ್ನೋದನ್ನ ನಾವೇನಾದ್ರೂ ಫೈಂಡ್ ಔಟ್ ಮಾಡಿದ್ರೆ that angle of rotation caused by an optically active compound is called specific rotation. Now you can define specific rotation in a very simple and very sweet manner as follows. Specific rotation is the angle of rotation. Alpha is the angle of rotation caused by an optically active compound with a solution concentration of 1 gram per cm cube with a solution length of 1 decimeter for a given wavelength at a constant temperature. I hope now you can understand. So this is the symbol for specific rotation. This specific rotation is given by alpha divided by L into C, where alpha is the angle of rotation which we are going to observe at the time of doing the experiment. Then alpha is the angle of rotation, L is the length of the solution, C is the concentration of the solution. So specific rotation is defined as it is the angle of rotation caused by an optically active compound with a solution concentration of 1 gram per cm cube with a solution length of 1 decimeter for a given wavelength at constant temperature. Then the specific rotation is given by alpha divided by L into C, where alpha is the angle of rotation which is observed at the time of doing the experiment, and L is the length of the solution which has been taken in the polarimeter tube, and C is the concentration of the solution. When we change any one among the four, there will be a change in the angle of rotation. Then the angle of rotation depends on concentration of the solution, length of the solution. It also depends on the wavelength of the plane polarized light what we are using, and it also depends the temperature at which the angle of rotation is determined. So that let me recall, specific rotation is defined as it is the angle of rotation caused by an optically active compound with a solution concentration of 1 gram per cm cube with a solution length of 1 decimeter for a given wavelength at constant temperature in a mathematical manner. So the specific rotation is given by alpha divided by L into C, where alpha is the lambda, so lambda is the wavelength of the plane polarized light, T is the temperature, alpha is the angle of rotation which is observed at the time of doing the experiment, L is the length of the solution, and C is the concentration of the solution. I hope the specific rotation is clear. So specific rotation depends on how many factors, means it depends on 4 factors. It depends on the concentration of the solution. When you change the concentration of the solution, there is a change in the specific rotation. It also depends on the length of the solution. Where there is a change in the length of the solution, there is a change in the specific rotation. It also depends on the wavelength of the plane polarized light what we are using at the time of doing the experiment. So, with change in the wavelength also changes the specific rotation, and change in temperature also changes the specific rotation. So that the specific rotation of any compound depends on the following 4 factors. So specific rotation is very simple and simply defined as follows. It is the angle of rotation caused by an optically active compound with a solution concentration of 1 gram per cm cube with a solution length of 1 decimeter for a given wavelength at constant temperature. Then, after knowing the specific rotation, very simple, you know very well, an optically active compound which rotates the plane polarized light in the clockwise direction or towards right is called dextrorotatory. Dextrorotatory is generally indicated by a sign plus, and an optical isomer which rotates the plane polarized light in anti-clockwise direction towards left is called levorotatory. So dextro is generally indicated by plus, and levo is generally indicated by minus. So dextro and levo are the two both are optically active, but they rotate the plane polarized light in the opposite direction. Now, the other thing is, let us consider one very simple reaction. The simple reaction is as follows. Let me take this is a ethyl bromide, which can be taken as bromide 10. When we react the same molecule with aqueous NaOH, which undergoes nucleophilic substitution reaction, so it is possible to get two different types of products. Two different types of products can be obtained when we subject ethyl bromide for nucleophilic substitution reaction by warming with aqueous NaOH. Let me, this is what B1 and this is what B2. Now, when the reaction follows, when the reaction proceeds, it is possible to get a product of this type. Look here, this is what, this is, sorry, a Br will be replaced by OH. This is OH, and this is H, and this is H, and this is the CH. This is one product, let me take a structure one. And it is also possible to get another product. This is OH, this is H, and this is CH3, and this is the OH. This is structure 2. So when ethyl bromide is warmed with aqueous NaOH to get ethyl alcohol, it is possible to get product structure 1 and structure 2. Let me take one by one. Suppose when we get only product 1 without getting product 2, that indicates that the orientation of atoms, groups and bonds in the reactant and the orientation of atoms, groups and bonds in the products, they remain same. Reaction ನಿಮ್ಮ ರಿಯಾಕ್ಟೆಂಟ್ ಮಾಲಿಕ್ಯೂಲ್ ಅಲ್ಲಿ ಎರಡು H ಒಂದು CH3 ಲೆಫ್ಟ್ ಗಿತ್ತು, ಇಲ್ಲೂ ಎರಡು H ಒಂದು CH3 ಲೆಫ್ಟ್ ಗೆ ಇದೆ, ಇಲ್ಲಿ ನೋಡಿ Br ರೈಟ್ ಗಿತ್ತು, OH ರೈಟ್ ಇದೆ. ಹಾಗಾದ್ರೆ ಇಲ್ಲಿ ನಿಮ್ಮ ಓರಿಯಂಟೇಷನ್ ಆಫ್ atoms, groups and bonds in the reactant molecule remains as it is when compared to the orientation of atoms, groups and bonds in the product. ಹಾಗಾದ್ರೆ ರಿಯಾಕ್ಷನ್ ನಡೆಯುವಂತ ಸಂದರ್ಭದಲ್ಲಿ ಡ್ಯೂರಿಂಗ್ ದ ಪ್ರೋಗ್ರೆಸ್ ಆಫ್ ದಿ ರಿಯಾಕ್ಷನ್ ಇಫ್ ದಿ ಓರಿಯಂಟೇಷನ್ ಆಫ್ atoms, groups and bonds remains same in the product as similar to the starting reactant molecule. ಅಂದ್ರೆ ನಮ್ಮ ರಿಯಾಕ್ಟೆಂಟ್ ಮಾಲಿಕ್ಯೂಲ್ ಅಲ್ಲಿ ಓರಿಯಂಟೇಷನ್ ಯಾವ ರೀತಿ ಇರುತ್ತೋ ಪ್ರಾಡಕ್ಟ್ ಅಲ್ಲಿ ಏನಾದ್ರೂ ಅದೇ ರೀತಿ ಇದ್ರೆ ಹಾಗಾದ್ರೆ ಆ ರಿಯಾಕ್ಷನ್ ನಡಿಬೇಕಾದ್ರೆ atoms, groups, bonds ಓರಿಯಂಟೇಷನ್ ಅನ್ನು ಹಾಗೆ ಉಳಿಸ್ಕೊಂಡಿದೆ ಅಂದ್ರೆ ರಿಟೈನ್ ಮಾಡಿದೆ. That is what we call retention of configuration. ಹಾಗಾದ್ರೆ ರಿಟೆನ್ಷನ್ ಆಫ್ ಕಾನ್ಫಿಗರೇಷನ್ ಅಂತ ಕರಿಬೇಕು ಅಂದ್ರೆ the orientation of atoms, groups and bonds of the reactant molecule should remain same in the product during the progress of the reaction. Then we used to say that the reaction has proceeded with the retention of configuration. Reaction has proceeded with the retention of configuration. The reaction has proceeded with the retention of configuration ಅಂತ ಅನ್ಬೇಕು ಅಂದ್ರೆ ರಿಯಾಕ್ಟೆಂಟ್ ಮತ್ತೆ ಪ್ರಾಡಕ್ಟ್ ಅಲ್ಲಿ ಆಟಮ್ಸ್ ಮತ್ತೆ ಗ್ರೂಪ್ಸ್ ಓರಿಯೆಂಟ್ ಆಗೋದು ಸೇಮ್ ಇರಬೇಕು. ನೋಡಿ ಇಲ್ಲಿ ಎಡಗಡೆಗಿತ್ತು ಎಡಗಡೆಗಿದೆ, ಬಲಗಡೆಗೆ ಇದೆ. ಹಾಗಾದ್ರೆ ರಿಯಾಕ್ಟೆಂಟ್ಸ್ ಅಲ್ಲಿ ಹೇಗಿತ್ತು ಪ್ರಾಡಕ್ಟ್ಸ್ ಅಲ್ಲೂ ಅದೇ ಇದೆ ಅಂದ್ರೆ ರಿಯಾಕ್ಷನ್ ನಡೆದಿರೋದು ಕಾನ್ಫಿಗರೇಷನ್ ಅನ್ನ ರಿಟೆನ್ಷನ್ ಮಾಡ್ಕೊಂಡು ಕಾನ್ಫಿಗರೇಷನ್ ರಿಟೈನ್ ಆಗಿದೆ ಅಂತ ಕರೀತೀವಿ. On the other hand, instead of getting structure 1, if we get structure 2, ನಮಗೆ ಏನಾದ್ರು structure 2 ಬಂದ್ಬಿಟ್ಟು ಅಂತಂದ್ರೆ ಈಗ ಒಂದು ಕೆಲಸ ಮಾಡೋಣ. ಇಲ್ಲಿ ನೋಡಿ ಎರಡು H CH3 ಲೆಫ್ಟ್ ಗಿತ್ತು, ಇಲ್ಲಿ ಎರಡು H CH3 ಲೆಫ್ಟ್ ಗೆ ರೈಟ್ ಹೋಗಿದೆ. ಅದೇ ನಮ್ಮ Br ರೈಟ್ ಗಿತ್ತು, ಅದೇ OH ಲೆಫ್ಟ್ ಗೆ ಬಂದಿದೆ ಅಂತ ಅಂದ್ರೆ the orientation of atoms, groups and bonds in the reactant and in the product they do not look similar. The orientation of atoms, groups and bonds in the product is exactly opposite when compared to the orientation of atoms, groups and bonds when in the reactant. Then we used to say that the reaction has proceeded. ಅಂದ್ರೆ ಈಗ ರಿಯಾಕ್ಷನ್ ನಡೆದಿರೋದು ಕಾನ್ಫಿಗರೇಷನ್ ಅನ್ನ ಹಾಗೆ ಉಳಿಸ್ಕೊಂಡಲ್ಲ, ಕಾನ್ಫಿಗರೇಷನ್ ಅನ್ನ ಇನ್ವರ್ಟ್ ಮಾಡ್ಕೊಂಡು ಹಾಗಾದ್ರೆ ತಿರುಗಿಕೊಂಡಿದೆ. That is what inversion of configuration. That is what we call as inversion of configuration. ರಿಯಾಕ್ಟೆಂಟ್ ಹೆಂಗಿರುತ್ತೋ ಪ್ರಾಡಕ್ಟ್ ಹಂಗೆ ಬಂದಿದೆ ಅಂದ್ರೆ ಕಾನ್ಫಿಗರೇಷನ್ ಅನ್ನ ರಿಟೈನ್ ಮಾಡ್ಕೊಂಡಿದೆ. ದಟ್ ಇಸ್ ವಾಟ್ ವಿ ಕಾಲ್ ರಿಟೆನ್ಷನ್ ಆಫ್ ಕಾನ್ಫಿಗರೇಷನ್. ರಿಯಾಕ್ಟೆಂಟ್ ಹೋಲಿಸಿದ್ರೆ ನಮ್ಮ ಪ್ರಾಡಕ್ಟ್ಸ್ ಅಲ್ಲಿ ಆಟಮ್ಸ್, ಗ್ರೂಪ್ಸ್, ಬಾಂಡ್ಸ್ ಅನ್ನ ಇನ್ವರ್ಟ್ ಆಗಿದೆ, ತಿರುಗಿಕೊಂಡಿದೆ ಅಂದ್ರೆ ದಟ್ ಇಸ್ ಕಾಲ್ಡ್ ಇನ್ವರ್ಷನ್ ಆಫ್ ಕಾನ್ಫಿಗರೇಷನ್. ಸೊ ಇಟ್ ಇಸ್ ಪಾಸಿಬಲ್ ಟು ಗೆಟ್ ಬೋತ್ ರಿಟೆನ್ಷನ್ ಆಫ್ ಕಾನ್ಫಿಗರೇಷನ್ ಆಸ್ ವೆಲ್ ಆಸ್ ಇನ್ವರ್ಷನ್ ಆಫ್ ಕಾನ್ಫಿಗರೇಷನ್. ಸ್ಟ್ರಕ್ಚರ್ 1 ಮಾತ್ರ ಬಂದಿದೆ, 2 ಬಂದಿಲ್ಲ ಅಂದ್ರೆ ದಟ್ ಇಸ್ ದ ರಿಟೆನ್ಷನ್ ಆಫ್ ಕಾನ್ಫಿಗರೇಷನ್. Structure 2 ಮಾತ್ರ ಬಂದಿದೆ, structure 1 ಬಂದಿಲ್ಲ ಅಂದ್ರೆ that is the inversion of configuration. I mean to say when we get only structure 1 without structure 2 then it is reaction has proceeded with the retention of configuration. On the other hand, when we get only the structure 2 without getting structure 1 then we used to say that the reaction has proceeded with the inversion of configuration. Now let me take a simple change in the model. Now let me replace this particular H by something like C2H5. This is C2H5. Now, this is also this molecule. Now, why I am changing, you will understand very easily. Let me take like this. This is your C2H5. This is your C2H5. Okay? Now, this is the molecule which contains 4 carbon atoms. Okay, there are 2 carbon atoms here, third carbon atom and 4th carbon atom. Similarly, 2 carbon atoms, 3 carbon atoms, 4 carbon atoms. When you observe very carefully, this is one particular carbon which is chiral carbon. Chiral carbon means which is bonded to 4 different atoms groups. Hydrogen ಬೇರೆ, bromine ಬೇರೆ, ethyl ಬೇರೆ, methyl ಬೇರೆ. ಇಲ್ಲೂ ಅಷ್ಟೇ ಹೈಡ್ರೋಜನ್ ಬೇರೆ, ethyl ಬೇರೆ, methyl ಬೇರೆ, OH ಬೇರೆ. ಇದು ಹೈಡ್ರೋಜನ್ ಬೇರೆ, ಈಥೈಲ್ ಬೇರೆ, ಮೀಥೈಲ್ ಬೇರೆ, OH ಬೇರೆ. ಹಾಗಾದ್ರೆ ಇದು ಕೈರಲ್ ಕಾರ್ಬನ್, ಹಾಗಾದ್ರೆ ಇದು ಕೈರಲ್ ಕಾರ್ಬನ್, ಇದು ಕೈರಲ್ ಕಾರ್ಬನ್ ಅಂತ ಅಂದ್ರೆ now when we carry out this particular chemical reaction by warming with aqueous NaOH, when you get equal volume, equal quantity, molar quantities. Let me take a mere example. Let us assume that I am going to start the reaction with 1000 molecules. 1000 molecules of reactants. So with 1000 molecules of reactant, I am going to add 1000 molecules of any OH. When the reaction proceeded, let us assume that we will get 500 of structure 1 and 500 of structure 2. ಹಾಗಾದ್ರೆ ಈ 1000ದಲ್ಲಿ 500 ಈ ತರದ್ದು ಬಂದು ಇನ್ನು 500 ಈ ತರದ್ದು ಬಂದಿದೆ ಅಂದ್ರೆ ನಮ್ಮ ಪ್ರಾಡಕ್ಟ್ ಅಲ್ಲಿ ಸ್ಟ್ರಕ್ಚರ್ 1 ಇದೆ, ಸ್ಟ್ರಕ್ಚರ್ 2 ಇದೆ. You can very easily observe structure 1 and structure 2. They are related with each other as an optical mirror image, which are nothing but your enantiomers, which are nothing but your optical isomers because of the presence of chiral carbon atom, as the molecule does not possess plane of symmetry. So structure 1 is optically active, structure 2 is also optically active. So they are optical isomers which are related with each other as an optical mirror image, and they are non-superimposable, and we can call them as enantiomers. And in a mixture which contains equal quantity or equimolar quantities of enantiomers, that mixture is called racemic mixture. Racemic mixture. Please remember, a mixture containing equimolar quantities, not equal quantities. Many students, they used to write equal quantity. No. Equimolar quantity. Let me take for example, let us say this is your dextroisomer and this is your levoisomer. So dextro and levoisomer are in equimolar quantities. A racemic mixture is defined as a mixture containing equimolar quantities of both plus and minus isomer of a compound. So a mixture containing equimolar quantities of both plus and minus isomers of a compound is called racemic mixture. And it is very simple. Racemic mixture is optically inactive. The optical inactivity of racemic mixture is called the rotation is because the rotation caused by one isomer is compensated by the other isomer. Racemic mixture optically inactive ಆಗುತ್ತೆ. Inactive ಯಾಕಾಗುತ್ತೆ? ಅದರಲ್ಲಿ structure 1 optically active, structure 2 is also optically active, but in the mixture we have both structure 1 and structure 2. ಈ ಎರಡನ್ನೂ ನಾವು ಈಕ್ವಿಮೋಲಾರ್ ಕ್ವಾಂಟಿಟೀಸ್ ಅಲ್ಲಿ ಮಿಕ್ಸ್ ಮಾಡಿಬಿಟ್ಟು ನಾವು ಏನಾದ್ರೂ ಆಪ್ಟಿಕಲ್ ಆಕ್ಟಿವಿಟಿ ನೋಡುವಂತ ಸಂದರ್ಭದಲ್ಲಿ ಸ್ಟ್ರಕ್ಚರ್ 1 ಏನ್ ಬಲಕ್ಕೆ ತಿರುಗಿಸುತ್ತೆ, ಸ್ಟ್ರಕ್ಚರ್ 2 ಎಡಕ್ಕೆ ತಿರುಗಿಸಿ ಆಂಗಲ್ ಆಫ್ ರೊಟೇಷನ್ 0 ಮಾಡಿ ನಿಲ್ಲಿಸುತ್ತೆ. ಹಾಗಾದ್ರೆ as the rotation caused by one isomer is compensated by another isomer, the net rotation becomes 0. When the net rotation becomes 0, the angle of rotation becomes 0. When the angle of rotation becomes 0, then we used to say that it is optically inactive. You can say anything which is optically active only when it rotates at least a small degree of rotation at the time of doing the experiment. Now racemic mixture ತಗೊಂಡು ಏನಾದರೂ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಮಾಡಿದ್ರೆ ಒಂದು ಐಸೋಮರ್ ಏನ್ ರೊಟೇಟ್ ಮಾಡುತ್ತೋ ಇನ್ನೊಂದು ಐಸೋಮರ್ ಅದನ್ನ ಉಲ್ಟಾ ಮಾಡಿ ಕಾಂಪನ್ಸೇಟ್ ಮಾಡ್ಬಿಟ್ಟು ರೊಟೇಷನ್ ನ 0 ಮಾಡುತ್ತೆ. ನಾವು ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಮಾಡಬೇಕಾದ್ರೆ polarimetry ನೋಡಿದಾಗ 0 ರೊಟೇಷನ್ ಕಾಣುತ್ತೆ. 0 ರೊಟೇಷನ್ ಕಾಣಿಸ್ತಾ ಇದೆ ಅಂದ್ರೆ ರೋಟೇಟೇ ಆಗಿಲ್ಲದೆ ಇರೋದನ್ನ ನಾವು ಆಪ್ಟಿಕಲಿ ಇನ್ಆಕ್ಟಿವ್ ಅಂತ ಕರಿತೀವಿ. So the racemic mixture is optically inactive because the mixture contains equimolar quantities of both plus and minus isomer. Since the rotation caused by one isomer is compensated by the other isomer is the main reason for the optical inactivity of racemic mixture. The racemic mixture is optically inactive because the rotation caused by one isomer is compensated by the another isomer, hence which is called the external compensation. Racemic mixture is optically inactive because of external compensation, hence the rotation caused by one isomer is compensated by the another isomer. So a definition is, of course, let me repeat once again, a mixture containing equimolar quantities of both plus and minus isomers of a compound which is optically inactive is called racemic mixture. Racemic mixture is optically inactive due to external compensation. The meaning of the external compensation is the rotation caused by one isomer is compensated by the another isomer. External one more molecule of the same isomer is responsible to make the angle of rotation 0 and to make the molecule optically inactive. So that racemic mixture, optical inactivity of racemic mixture is because of external compensation. So a mixture containing equimolar quantities of both plus and minus isomers of the same compound which is optically inactive is known as racemic mixture. Racemic mixture is optically inactive because of external compensation. That is, the rotation caused by one isomer is compensated by the another isomer of the same compound. Let me move on to the other fundamental part of the topic, diastereomers. Diastereomers. Remember, we have already learned enantiomers. So enantiomers are the optical isomers, which are related with each other as an object under image and non-superimposable on one. To learn about diastereomers, let me take a simple example, tartaric acid. So let's say this is our tartaric acid. This is OH, 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 sorry, H, this is H. As we have already learned, so though it is a 4-carbon compound, there are only 2 chiral carbons. This is chiral carbon and this is chiral carbon. According to Van 't Hoff, when the molecule contains 2 chiral carbon atoms, the number of possible isomers given by the simple mathematical relation 2 to the power of n, this is 2 to the power of 2, 2 to the power of 2 is 4 isomers. 4 isomers, out of 4 isomers, 1 is on the board. Let us structure 1. When we want to get the structure 2, so it is nothing but the mirror image of the structure 1. This is COOH, this is C, COOH, look here, this is OH. ಯಾಕಂದ್ರೆ ನೀವು ಸ್ಟ್ರಕ್ಚರ್ 1 ಅನ್ನು ಮಿರರ್ ನೋಡಿದ್ರೆ ನಿಮಗೆ ಏನಾಗುತ್ತೆ ಕ್ಲಿಯರ್ ನೋಡಿ. This is structure 2. When 4 isomers are possible, 4 isomers chances ಇದೆ ಅಂದಾಗ 2 ಮಾತ್ರ ಇದಾವೆ. ಹಾಗಾದ್ರೆ ಮೂರನೇದು ಯಾವುದು ಸರ್? ಮೂರನೇ ಮಾಲಿಕ್ಯೂಲ್ ಬರೀತಾ ಇದೀವಿ ನೋಡಿ. This is what the third possible structure for your tartaric acid. Let me write, this is OH, this is H, and this is H, this is OH. What the difference is? In the structure 1, both the OH groups are in the same side. In the structure 2 also, both the OH groups are in the same side, but it is a mirror image of the structure 1. So this is what the structure 3, where the 2 OH groups are not in the same side. They are in the opposite direction. Coming to the last, the structure 4 is the mirror image of the structure 3. So this is what? This is COOH, this is C, this is C, this is COOH, and remember, this is OH, this is H, and this one is OH, and this one is H. So, all the 4 molecules are on the board, which are possible for our tartaric acid. They are because the molecule contains 2 chiral carbon atoms, therefore 4 structures are possible. All the 4 structures are there on the board, and they are labeled as structure 1, structure 2, structure 3, and structure 4. Now, let me take structure 1 and 2. If we take structure 1 and 2, remember, structure 1, if you observe, if you divide the molecule through this particular plane, it gives 2 identical halves, which are related with each other as an object and mirror image, and they are non-superimposable on one another. Hence, the molecule is having a plane of symmetry. When the molecule is having a plane of symmetry, this molecule is optically inactive. Optically inactive. The optical inactivity of structure 1 is because of the presence of plane of symmetry, and the same explanation holds good for your structure 2 also. Structure 1 and structure 2 are optically inactive because of the presence of plane of symmetry. Whereas structure 3, look here, when we divide the molecule through this particular plane, it divides the molecule into 2 identical halves, but they are not related with each other as an object under image. That is how, if you hold the mirror like this, if you hold the mirror like this, we should be able to see this OH here. Now mirror thing irkandre ee OH illi kaanbeku, namage kaanta irodu nodi ee OH illi kaanadi, illi OH aithe ಕನ್ನಡಿಯಲ್ಲಿ ನೋಡಿದ್ರೆ ಈ OH ಮೇಲೆ ಕಾಣಬೇಕು ಅಂದ್ರೆ ನಮಗೆ H ಕಾಣ್ತಾ ಇದೆ ಅಂತಂದ್ರೆ ಇದು ಆಬ್ಜೆಕ್ಟ್ ಆಫ್ ಇದು ಮಿರರ್ ಇಮೇಜ್ ಅಲ್ಲ. ಆಬ್ಜೆಕ್ಟ್ ಮಿರರ್ ಇಮೇಜ್ ರಿಲೇಷನ್ ಇಲ್ಲ ಅಂದ್ರೆ ಇದಕ್ಕೆ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇಲ್ಲ. ಇದಕ್ಕೆ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮಿಟ್ರಿ ಇಲ್ಲ. ಹಾಗಾದ್ರೆ absence of plane of symmetry and this becomes optically active. Structure 1 and structure 2 are optically inactive, whereas structure 3 and structure 4, so this is also not having plane of symmetry. ಹಾಗಾದ್ರೆ structure 3 and 4 active plane of symmetry ಇಲ್ಲ ಅಂತಂದ್ರೆ ಇವೆರಡು optically active. ಇವೆರಡು optically active ಅನ್ನೋದಾದ್ರೆ, of course, let me take this as a dextro and this as a lead. Right? Now, structure 3 and structure 4 are enantiomers because they are optical isomers which are related with each other in an object and mirror image, and they are non-superimposable on one another. Therefore, structure 3 and structure 4 are nothing but enantiomers. Now, let me take, observe very carefully, structure 1 and structure 3. Now I am taking these. These two, remember, this is optically, because of the absence of plane of symmetry, this is optically active. Whereas, because of the presence of plane of symmetry, this is optically inactive. ಹಾಗಾದ್ರೆ ಇದು ಆಕ್ಟಿವ್ ಆಗಿದೆ, ಇದು ಇನ್ಆಕ್ಟಿವ್ ಆಗಿದೆ ಅಂತಂದ್ರೆ ಇದು ಆಪ್ಟಿಕಲ್ ಐಸೋಮರ್, ಇದು ಆಪ್ಟಿಕಲ್ ಐಸೋಮರ್ ಅಲ್ಲ. ಹಾಗಾದ್ರೆ ಎರಡೂ ಆಪ್ಟಿಕಲ್ ಐಸೋಮರ್ಸ್ ಆಗಿದ್ರೆ ಆ ಆಪ್ಟಿಕಲ್ ಐಸೋಮರ್ಸ್ ಅಂತ ಕರಿಬಹುದು. ಹಾಗಾದ್ರೆ ಇವೆರಡನ್ನು ತಗೊಂಡಾಗ ಅವು ಆಪ್ಟಿಕಲ್ ಐಸೋಮರ್ಸ್ ಅಲ್ಲ. ಹಾಗಾದ್ರೆ ಏನ್ ಮಾಡ್ತೀರಾ? ವಿತ್ ಸೇಮ್ chemical composition, with same molecular formula. Remember, those which differ in the orientation of atoms and groups in the space are called their stereoisomers. Okay, structure 1 and 3 are the stereoisomers. Structure 3 and 4 they are optical isomers. Now, structure 1 and 3 are the stereoisomers. Because with same molecular formula, they differ in the orientation of atoms and groups in the three-dimensional space. ನೋಡಿ ಎರಡು OH ಇಲ್ಲಿ ಒಂದೇ ಕಡೆ ಇದೆ, ಇಲ್ಲಲ್ಲ, ಇಲ್ಲಿ ನೋಡಿ ಒಂದು OH ಲೆಫ್ಟ್ ಇದೆ, ಒಂದು OH ರೈಟ್ ಇದೆ. ಮಾಲಿಕ್ಯುಲರ್ ಫಾರ್ಮುಲಾ ಸೇಮ್ ಇದ್ದು, ಸ್ಟ್ರಕ್ಚರಲ್ ಫಾರ್ಮುಲಾ ಸೇಮ್ ಇದ್ದು, ತ್ರೀ-ಡೈಮೆನ್ಷನಲ್ ಸ್ಪೇಸ್ ಅಲ್ಲಿ ಆಟಮ್ಸ್ ಮತ್ತು ಗ್ರೂಪ್ಸ್ ಏನಾದರೂ ಓರಿಯೆಂಟ್ ಆಗೋದು ಚೇಂಜ್ ಆಯ್ತು ಅಂದ್ರೆ they are the stereoisomers. Now, structure 1 and 3 are the stereoisomers. Stereoisomers. ಹಾಗಾದ್ರೆ ಮೊದಲನೇ ಕಂಡೀಷನ್ ಸಿಗ್ತಾ ಇದೆ, ಎ ಪೇರ್ ಆಫ್ ಎಕ್ಸ್ ಅಂಡ್ ಎ ಪೇರ್ ಎರಡು ಮಾಲಿಕ್ಯೂಲ್ ಇದೆ, ಎರಡನ್ನ ನಾವು ಪೇರ್ ಅಂತ ಕರ್ಕೊತೀವಿ. ಎ ಪೇರ್ ಆಫ್ ಸ್ಟೀರಿಯೋಐಸೋಮರ್ಸ್. ಲುಕ್ ಹಿಯರ್, ಸೆಕೆಂಡ್ ಒನ್, ಇದು ಆಬ್ಜೆಕ್ಟ್ ಆದ್ರೆ ಇದು ಮಿರರ್ ಇಮೇಜ್ ಅಲ್ಲ. ಇದಕ್ಕೆ ಆಬ್ಜೆಕ್ಟ್ ಇದೆ, ಇದು ಆಬ್ಜೆಕ್ಟ್ ಆದ್ರೆ ಸ್ಟ್ರಕ್ಚರ್ 2 ಮಿರರ್ ಇಮೇಜ್, ಸ್ಟ್ರಕ್ಚರ್ 3 ಅಲ್ಲ. ಹಾಗಾದ್ರೆ ಸ್ಟ್ರಕ್ಚರ್ 1 is not related with each other with structure 3 as a mirror image. Structure 1 and 3 they are not related with each other as a object and mirror image. Also, they are the stereoisomers, not related as object and mirror image. Second condition, not related with each other as an object and mirror image. The third condition, which are non-superimposable. Remember, there are three conditions. A pair of stereoisomers, not related with each other as an object and mirror image. This object ಆದ್ರೆ ಇದನ್ನ ಕನ್ನಡಿಯಲ್ಲಿ ನೋಡಿದಾಗ ಈ ತರ ಕಾಣಲ್ಲ, ಇದನ್ನ ಕನ್ನಡಿಯಲ್ಲಿ ನೋಡಿದಾಗ ಈ ತರ ಕಾಣಲ್ಲ ಅಂತಂದ್ರೆ ಆಬ್ಜೆಕ್ಟ್ ಮತ್ತು ಮಿರರ್ ಇಮೇಜ್ ರಿಲೇಷನ್ ಇಲ್ಲ. ಹಾಗಾದ್ರೆ a pair of stereoisomers not related with each other as an object and mirror image and non-superimposable on one another are called diastereomers. I hope you can easily differentiate enantiomers and diastereomers. ನೋಡೋಣ, ಹಾಗಾದ್ರೆ enantiomers ಮತ್ತೆ diastereomers ಅನ್ನು ಡಿಫರೆನ್ಶಿಯೇಟ್ ಮಾಡಬೇಕಾದ್ರೆ ಇಲ್ಲಿ a pair of optical isomers, ನೋಡಿ a pair of optical isomers, ಇಲ್ಲಿ a pair of stereoisomers. Don't forget, it is very interesting. There is a difference in the first condition. So, a pair of optical isomers, a pair of stereoisomers, related with each other as an object and mirror image, not related with each other as an object and mirror image. Object to mirror image relation irutte, object to mirror image relation iralla. Non-superimposable. Third condition is same. But first and second conditions are different. A pair of optical isomers, a pair of stereoisomers, related with each other as an object and mirror image, not related with each other as an object and mirror image, non-superimposable on one another. Any molecule which satisfies these three conditions can be called as enantiomers. Any molecule which satisfies these three conditions are called diastereomers. Therefore, structure 1 and 3 are called diastereomers. A pair of stereoisomers, not related with each other as an object and mirror image, and non-superimposable on one another are called diastereomers. Therefore, structure 1 and 3 diastereomers, structure 1 and 4 diastereomers, structure 2 and 3 diastereomers, structure 2 and 4 diastereomers, structure 3 and 4 they are enantiomers. Structure 1 and structure 2, they are mesoisomers. Mesoisomers are optically inactive even with chiral carbon atom. ನೋಡಿ chiral carbon atom ಒಂದಲ್ಲ ಅಂತ ಹೇಳ್ತಿದ್ದೀವಿ. chiral carbon atom ಒಂದಲ್ಲ ಅಂತ ಎರಡು ಇದ್ರೂ ಸಹ these two 1 and 2 becomes optically inactive because rotation caused by half of the molecule is compensated by rotation half of the another half of the same molecule. ಅರ್ಧ ಮಾಲಿಕ್ಯೂಲ್ ಏನು ರೊಟೇಟ್ ಮಾಡುತ್ತೋ ಅದರಲ್ಲೇ ಇರ್ತಕ್ಕಂಥ ಇನ್ನರ್ಧ ಮಾಲಿಕ್ಯೂಲ್ ಅದನ್ನ ಕಾಂಪನ್ಸೇಟ್ ಮಾಡುತ್ತೆ. ಹಾಗಾದ್ರೆ ಇಲ್ಲಿ ರೊಟೇಟ್ ಮಾಡ್ತಕ್ಕಂಥ ಒಂದು ಆಂಗಲ್ ಆಫ್ ರೊಟೇಷನ್ ಅನ್ನ ಕಾಂಪನ್ಸೇಟ್ ಮಾಡ್ಲಿಕ್ಕೆ ಹೊರಗಡೆಯಿಂದ ಯಾರು ಬರ್ತಾ ಇಲ್ಲ, ಎಕ್ಸ್ಟರ್ನಲ್ ಇಂದ ಯಾರು ಎಂಟರ್ ಆಗ್ತಾ ಇಲ್ಲ, ಅದರಲ್ಲೇ ಇರ್ತಕ್ಕಂಥ ಅರ್ಧ ಮಾಲಿಕ್ಯೂಲ್ ಕಾಂಪನ್ಸೇಟ್ ಮಾಡಿ ಆಪ್ಟಿಕಲಿ ಇನ್ಆಕ್ಟಿವ್ ಆಗೋದ್ರಿಂದ ಅದನ್ನ ಇಂಟರ್ನಲ್ ಕಾಂಪನ್ಸೇಷನ್ ಅಂತೀವಿ. ಹಾಗಾದ್ರೆ in any molecule, even with chiral carbon atom, because of the presence of the plane of symmetry, due to internal compensation, if the molecule becomes optically inactive, such compounds are called meso compounds. Remember, structure 1 and 2 are called mesoisomers. A pair of compounds or any chemical compound, even with chiral carbon atom, it becomes optically inactive because of the presence of plane of symmetry due to internal compensation. Internal compensation means the rotation caused by half of the molecule is compensated by another half of the same molecule. ನೋಡಿ ಅರ್ಧ ಮಾಲಿಕ್ಯೂಲ್ ಬಲಕ್ಕೆ ಅಂತ ಅರ್ಧ ಮಾಲಿಕ್ಯೂಲ್ ಬಲಕ್ಕೆ ಅಂತ ಹಿಂಗೆ ಹೇಳಿದ್ರೆ ಇನ್ನು ಅರ್ಧ ಮಾಲಿಕ್ಯೂಲ್ ಎಡಕ್ಕೆ ಅಂತ ಹಿಂಗೆ ಹೇಳುತ್ತೆ. ನೆಟ್ ರೊಟೇಷನ್ ಎಷ್ಟು? 0. ರೊಟೇಷನ್ ಏನಾದ್ರೆ 0 ಆದ್ರೆ we used to say that it is optically inactive. ಹಾಗಾದ್ರೆ mesoisomers are optically inactive due to internal compensation. It is because the rotation caused by half of the molecule is compensated by another half of the same molecule. Okay, let me stop at this stage and let me continue the remaining part in the next class. Thank you. ಕರೆಕ್ಟಾಗಿ ಬಂದ್ಬಿಟ್ಟಿದ್ರಲ್ಲ ಅದ್ರು ಎಕ್ಸಾಕ್ಟ್ ನಾಟ್ ಸೆಕೆಂಡ್ ಇಲ್ಲೇ ಇವತ್ತು ನಾನು ಇವತ್ತಿಂದು ಕ್ಲಾಸ್ ಜರ್ಕಿನ ಹಾಕೊಂಡಿದ್ದೀನಿ.